Today I'm going to talk about essentially a story of emergent critical gauge theory out of a lattice spin system or out of lattice spin systems in 2+1 dimensions. So roughly my talk will consist of two parts. They're intimately related. So the first part I'll cover some earlier works done with these folks, Xue Yang and Ashwin from Harvard, and my colleague Ying Chen from Perimeter. If I have time, hopefully, I'll talk about some more recent follow-up developments done with this student, Vladimir Kovra, who was a former Perimeter master student, now doing his PhD at Stanford. So I want to talk about emergent critical gauge theories out of quantum magnetism, right? So if I so quantum magnetism in general is a very hard topic because it's kind of intrinsically a strongly coupled system. So if you take some quantum, let's say Heisenberg model, for example, on the triangular lattice. Right? Take Heisenberg model, maybe with some further neighbor, more complicated term. Let's say, for example, with one spin half per site on the lattice. It's not clear at all a priori how you actually solve it. So there's the classic approach known as the mean field theory, in which you just assume that the system magnetically orders. So you put in some expectation value in the spin and then solve essentially a one-body problem self-consistently. But by now it is well appreciated that you miss a lot of interesting quantum phases of matter with this approach. Especially you miss those states that are highly entangled. So one way people established over the past several decades to try to overcome this shortage is to consider doing mean field theory, but in a funnier basis. Right? So this is something known as the parton trick in condensed matter physics. The idea is very simple. You just, instead of dealing directly with the spin operator, you rewrite the spin operator this way, where sigma is the Pauli matrix, and this F operator is a fermion operator, is an auxiliary fermion operator that transforms as spin half as the SU2 fundamental. So this formally is a exact rewriting if you impose the right constraint. Here the right constraint being having exactly one fermion occupied at every lattice site. That way you recover the spin one half Hilbert space. So if you do this, now you can make a mean field ansatz, not directly in terms of the spin, but in terms of the fermion themselves. Okay? So the procedure is to consider a mean field theory, which is basically just a fermion hopping problem on the lattice, right? With some hopping parameter Tij chosen self-consistently. So in principle, this hopping parameter Tij can be chosen quite arbitrarily. But it turns out there, at least in some cases, it's appropriate to choose the hopping Tij so that at low energy, you have emergent gapless Dirac fermions out of this auxiliary F fermions. So these F fermions, I'll call them spin-ons in the rest of the talk. Okay. This can be done essentially on any 2D lattice you like. For example, on triangular lattice, you can choose the Tij such that you have a pi flux on every downward triangle and 0 flux on every upward triangle. And then you solve the tight binding model. You realize that at low energy, you get 2 gapless Dirac nodes in momentum space. And since the F fermions transform as spin half as a SU2 fundamental, you get an additional twofold multiplicity. So you in total get 4 Dirac cones at low energy. So this type of mean field theory has some historical motivation back in the 80s and 90s. But over the past several years, it's been well appreciated that they may actually be indeed be relevant for reasonably realistic models. Okay. But of course, you don't stop there. You don't just stop at some free Dirac fermions. What makes them really interesting is that by doing this, what you actually get is an emergent gauge theory. And this can be seen directly already from this parton decomposition. You can see this rewriting introduce some redundancy. For example, if you redefine your F fermions by a phase factor, the phase can be different on every lattice site. There's absolutely nothing happens physically, right? Because the two cancels here. What that means is that there is a U1 gauge redundancy for this spin-on fermion this way, which means if I go to low energy, what I get necessarily is a U1 gauge theory, right? Because a local U1 rotation symmetry is basically a gauge symmetry. And the gauge charge is defined as basically my fermion charge, my fermion occupation number, -1. So this -1 is really just saying that if I want to recover my physical spin Hilbert space, which is a spin half per lattice site, then I should set this gauge charge to 1, meaning I have a fermion occupation number equal to 1 on every site. So recall that 1 fermion recovers the spin half local Hilbert space. Okay. So recall that previously the mean field theory I considered gives you some number of Dirac fermions. So now if you couple that to an additional dynamical emergent U1 gauge field, what you end up getting is a continuum field theory, as a well-known continuum field theory, but now in 2+1 dimension, which is basically a quantum electrodynamics. So you get, in this case, 4 gapless Dirac fermions coupled to a dynamical U1 gauge field, little a. So the continuum action can be written this way. So when I write a Lagrangian like this, you should always think that, you can always add a Maxwell term, but I'm just suppressing that for notational convenience here. Okay. And by the way, when I say 4 Dirac fermion, the way I'm counting it is that each Dirac fermion is 2 components. So this theory, unlike the 4D version of QED, which is the textbook example of quantum field theory, the 3D version is actually strongly coupled in the IR. So it's actually pretty non-trivial to study its IR fate. But what we know from current numerical simulation is that at least for this flavor number, it's quite likely that the theory flows to a non-trivial conformal field theory at low energy. So basically the theory is the free Dirac fermion theory is gapless, and with when coupled to a U1 gauge field, the theory remains non-trivially gapless even at low energy. So that gives you potentially a realization of a critical spin liquid, critical phase at low energy. And so an important class of objects in this 3D quantum electrodynamics is known as the monopoles. So whenever you have a dynamical U1 gauge field in 3 dimension, in 2+1 dimension, they tend to play some important role. So you can think of the monopole operator as basically it's defined as an operator that inserts some 2-pi flux of the emergent U1 gauge field. So the other way to say it is that it's charged under an emergent U1 symmetry, which correspond to the conservation of the gauge flux. What's special about QED3, about Dirac fermion, is that whenever you have a 2-pi flux, there will be a zero mode trapped for each flavor of Dirac fermion. So this is well known. Well, this is basically the zeroth, the famous zeroth Landau level for the Dirac fermion. Okay. And for a reason that I'm not going to explain in detail, that turns out if you want a gauge invariant state, if you want to consider a gauge invariant monopole operator, you should for the ground state, you should half fill the zero modes. So for example, in this case, we have 4 flavors of Dirac fermion. So you should fill 2 of the 4 Dirac fermions. And that gives you in total 6 different ways of having invariant monopole operator. And remember, we have 4 Dirac fermions, so the flavor symmetry, the maximal flavor symmetry you can have is SU4. So these 6 monopoles are transformed as nothing but the vector representation in the SU4, which is basically SO6. So these are the fundamental order parameters of the theory in some sense. So one problem that's that was there, well, for quite a while was pretty non-trivial, was that so there's the monopole operator, there are 6 of them. How do they exactly transform under microscopic physical symmetries? Right. So in general, if I have a symmetry element G, let's say spin rotation, lattice translation, or rotation, or something, when acting on this monopole operator, it can act in this way. So this OIJ is an SO6 rotation matrix. And then there's a phase factor, additional phase factor, because monopole operator is complex. You can create a 2π flux. You can also just create a minus 2π flux. Okay. So there's a U1 rotation that's allowed. So for each symmetry element, it's relatively straightforward to figure out what is this O matrix, because it's decided by essentially how the zero modes transform under the microscopic symmetries, which is in turn decided by how the Dirac fermions or the lattice spin-on fermions transform under microscopic symmetries, which is relatively easy to figure out. What was harder is that it was how to decide this U1 phase factor. Okay? So you can phrase this as a more general question. So conceptually, the question is, I have some lattice scale symmetry here, which I call GUV, and I have some emergent critical theory at low energy, which tend to have a larger emergent symmetry than the UV symmetry. So in this case, my IR symmetry has SO6 or SU4, and there's a U1 symmetry that corresponds to the conservation of the gauge flux. You don't worry about the mod Z2 here, and things like charge conjugation and parity and so on. So how does this GUV embed into this GIR? So this symmetry embedding problem is in fact for any lattice system that gives you an interesting IR field theory, this is an important problem. Except for simple theories like Ising model, it's important, but it's also trivial. For example, in Ising model, the 5-4 scalar phi that appears in the IR is basically a coarse-grained version of the lattice Z2 spin. So it's relatively easy to figure out how UV symmetries that act on your lattice spin should act in the IR continuum field. But this problem becomes much more subtle if the IR theory has non-trivial topological disorder operators, things like vortex or monopoles, because those do not correspond to any simple coarse graining of some lattice spin degrees of freedom. Okay. So for lattice QED, the problem can be phrased more concretely as you have some monopoles, some pattern of the U1 gauge field moving in some charged Dirac sea. Right? So as you move, for example, by lattice translation or rotation, there will be some non-trivial Berry phase that's being accumulated. So, and that non-trivial Berry phase gives you some non-trivial lattice momentum and angular momentum. So it wasn't clear exactly how to really think about this problem. Essentially, when the monopole moves, the entire Dirac sea feels it. And in the past, there has been partial success. At the end of the day, you have to rely on numerics. So conceptually, it wasn't completely clear what was going on. So let me also say a bit about why we care about this problem. I explained to you why this problem is not entirely trivial, but why do we care? Well, okay, so first, conceptually, this is a necessary information to really characterize the state, right? In principle, it's not enough to just say, I have this UV system and I have an IR emergent field theory. I also have to specify how exactly does the UV symmetry act in my IR field theory. But more practically, it determines the monopole symmetry properties determine quite a number of non-trivial things. Maybe the most important one is whether the Dirac spin liquid can even exist as a stable critical phase of matter, because we know that the lowest monopole, the monopole that creates 2-pi flux, is almost certainly relevant in the RG sense. So the scaling dimension from various estimation, both large N and lattice Monte Carlo, indicate that the scaling dimension is well below 3. So it's certainly a relevant perturbation. So if your microscopic symmetry allows this monopole as a perturbation, then your Dirac spin liquid is not going to be stable. And it comes with various measurable consequences. For example, the monopole symmetry property will have some non-trivial signature in, for example, neutron scattering spectroscopy. It also determines what nearby symmetry breaking orders you get if you drive the system to a symmetry breaking phase. And let me briefly tell you how we solve this problem. So you can find more details in our paper. So it turns out the way to solve it is to use a set of techniques developed from another corner in condensed matter physics over the past 2 decades, which is band topology. Essentially, when I mentioned that the monopoles moving in that Dirac sea accumulate some Berry phase, and the entire Dirac sea feels it. Already, you sort of can feel that this has to somehow has to do with the topology of the field Dirac sea, and that turns out to be indeed true. So what you can do, for example, is imagine first having some mass term for your Dirac fermion. In this case, you can have what is known as the quantum spin Hall mass term. So it's a mass term which is positive for, let's say, spin up Dirac fermions and negative for spin down Dirac fermions. So this breaks spin rotation, but not lattice symmetry. And the monopole and this the symmetry breaks the SU4 flavor rotation. It turns out it also picks out one of the 6 monopoles as the ground state, as the lowest monopole, which is this. Okay. And if you examine the symmetry property of the monopole, for example, you will find that the monopole carries SZ quantum number +1, which means the monopole now behaves like an SX plus ISY, so S plus. So this already looks like a non-collinear magnetic order, right, on the lattice. So this kind of technique has been developed in the community over the past decade. And the next question, which is a bit more nagging, is that how do you think about lattice symmetries on this problem? So how does the monopole transform under various lattice symmetries in this case? So I'll be brief about how to do this, but the basic statement is that it's also decided by the underlying topology of the spin-on insulator. So it's now a quantum spin Hall insulator, but so when we say quantum spin Hall, it's about spin rotation and charge conservation. But you can generalize that to crystalline symmetries, and people have figured out how to do it in the band topology community. So the brief idea is this: you deform this gap fermions, the gap fermion, to some trivial limit, to some atomic limit, using techniques developed in band topology. So there will be a well-defined recipe to figure out exactly what type of atomic insulator it will develop, you will deform to. So when I say atomic insulator, you basically think of the fermions as some localized charged objects, some localized orbits in some real space points on the lattice. Right? For example, if you do it on the triangle lattice, if you take this quantum spin Hall insulator on the triangle lattice and deform it, try to deform it to a atomic insulator while preserving all the lattice symmetries, you get the picture that looks like this. So what you end up getting is one fermion at each lattice site, one fermion on each upward triangle center, and -1 charge on each downward triangle center. So you end up getting a simple picture like this. And once you get this picture, it becomes relatively easy to figure out how the monopoles transform under various lattice symmetries. For example, if you want to ask how does the monopole transform under C3, meaning a 2π/3 rotation around, for example, this upward triangle center, then you just realize there's one charge localized at this triangle center. So every time you do a 2π/3 rotation for the monopole essentially sees a Berry phase, a Haronov-Bohm phase. That's E times M. So M is the magnetic charge, E is the electric charge localized at the center. So upward triangle C3 gives you a phase factor of E to the 2π/3, right? And likewise, for downward triangle C3 rotation, you get a -2π/3 phase factor. So once you get all the rotation symmetry quantum numbers, you can also get translation just by composing rotations around different points. For example, you first perform a downward triangle C3 rotation, and then you perform an upward triangle inverse C3 rotation. That way you get a translation, and then you just multiply these two phases together and realize that under translation you also get a 2π/3 phase factor. So that's how you figure out how the monopoles transform under various lattice symmetries. So if you stare at this symmetry eigenvalues together with the fact that the monopoles behave as Sx plus Sy, if you stare at this pattern long enough, you realize that this describes nothing but the familiar 120-degree non-collinear antiferromagnetic order on the triangle lattice. Right? For example, you look at this pattern, you translate by one lattice unit, this rotates by some 2π/3. Okay, so that's basically how you figure out the monopole symmetry quantum numbers, and here's the result. So you can just generalize it, do a more careful calculation. The overall picture for SU2 system, and specifically spin 1/2 per site, is that on triangular and Kagame lattices, turns out the simplest Dirac spin liquid theory you can write down indeed do not have relevant monopole provisions that are allowed by microscopic symmetry. So all the relevant monopoles you can write down will be forbidden either by the spin rotation or lattice rotation or translation symmetries, right? Which means this Dirac spin liquid indeed can exist as a non-trivial stable critical phase on this lattices. On the other hand, on lattices like square or honeycomb, it turns out if you do the calculation, there will be a monopole operator which transforms trivially under all microscopic symmetries. So as a result, as a consequence, we don't expect the U1 Dirac spin liquid to be stable on those lattices, and this happens to be to agree well with what people have observed numerically. For example, for example, the U1 Dirac spin liquid has only been found numerically well on the triangle or Kagame lattices. Okay. Let me also say that the non-trivial symmetry quantum numbers on monopoles also have non-trivial consequence, even just for the Dirac spin liquid itself, even beside the fact that it's now stable, because they still exist as non-trivial critical operators or critical fluctuations in the theory. For example, if you do neutron scattering, measure spin-spin correlation function, they do show up in your spectrum. For example, on the triangle lattice, the consequence is that you get a non-trivial spectral weight at various non-trivial moments. If, for example, the 120-degree order, the fluctuating 120-degree order shows up as some non-trivial weight at the Brillouin zone boundary on the triangle lattice. Right? So this has been observed numerically on the triangular J1, J2 spin 1/2 Heisenberg model in these two papers. Probably to a less certain degree, maybe hopefully experimentally in this material. I mean, that we have to wait and see further confirmation. Okay? So what's being observed here is some apparent accumulation of spectral weight also at the K momentum without any apparent spin ordering. So now let me, with my remaining time, briefly mention this some more recent development. So once you figure out how things work for SU2 spin, it's kind of rather, at least conceptually, quite straightforward to generalize it to any arbitrary group, really, SU4 or anything. So so SU4 here has some reasonably realistic motivation here, because what it describes is that instead of just having a spin degree of freedom, you also have a two-level orbital degree of freedom. Right? Imagine you have some spin orbital system. So it's probably the simplest generalization of the SU2 Heisenberg model to SU4 system is some model like this, right? So where S and T are both some SU2 generators. So turns out when you write it this way, the system, the symmetry is enlarged from SU2 cross SU2 to SU4, right? So there is a particularly interesting model which has attracted some attention over the past, well, it's almost a decade, which is you put an SU4 fundamental, SU4 spin in the fundamental representation on every side of a honeycomb lattice in two dimension. And then you write down this model. So numerically, it was found that the ground state doesn't seem to order. In fact, it looks like a critical spin liquid. So the most obvious candidate is some kind of Dirac spin orbital liquid. So the minimum theory of this kind of Dirac spin orbital liquid for the SU4 spin is actually quite simple. It's a very straightforward generalization of the SU2 case. So the idea is you rewrite the SU4 generators here again as some bilinear combination of some spin-on, some auxiliary fermion operator. So T is it's just a matrix that represent the SU4 generator, and F, importantly, lives in the fundamental representation of SU4. Okay? And again, this kind of rewriting introduces a U1 gauge redundancy, because you can now again redefine the F fermion by a phase rotation. So you get a U1 gauge theory, and again, the gauge charge is defined as fermion occupied number -1. So -1 because, again, to get the F lives in the SU4 fundamental, and my physical Hilbert space has one SU4 fundamental per site. So to recover the Hilbert space, I want one fermion occupied per site. Okay. And again, you can get a Dirac, you can get a mean field theory that gives you Dirac fermions by putting a pi flux on every plaquette of the honeycomb model. So this is not the same as the graphene. The thing is, when the F fermions live in the SU4 fundamental, so having one fermion per site is not a half filling, but a quarter filling. So we should look at this point in momentum space. So it turns out if you have pi flux per honeycomb plaquette, at quarter filling, you'll end up having 2 Dirac fermions. Well, they appear at the same momentum in the reduced Brillouin zone. Okay. So now what you have, again, you have some number of Dirac fermions coupled again to a dynamical U1 gauge field. So the low energy effective theory is again a QED3, but now with fermion flavor NF equal to 8 instead of 4, because you have now 4 times 2. 2 from fermion doubling, that you have 2 valleys in the momentum space, and 4 from SU4 degeneracy. And numerically, the Gauss-Euler projected wave function you get out of this mean field theory appears to behave pretty well. It compares well to for example, things like exact diagonalization and so on. So it's tempting to say that maybe that's the theory. Everything looks fine, but there is one problem, which is if you do a careful calculation of the monopole symmetry properties in the way that I described earlier for the SU2 spin, the recipe I described earlier, at least conceptually, is quite straightforward to generalize to this SU4 case. I mean, practically, the calculation is a bit tedious, but conceptually, it's rather straightforward. What you find is that there is actually a monopole operator which is symmetry allowed. So there is one very specific monopole operator which transforms trivially under all microscopic symmetries. The SU4, lattice rotation, translation, reflection, time reversal, and so on. And from quite reliable either large N or numerical calculation, this monopole operator has dimension roughly 2.1, so it's definitely relevant. Which means this minimum U1 Dirac spin orbital liquid cannot really make sense, cannot really literally make sense. So it will be unstable, driven by the monopole symmetry allowed monopole perturbation. We don't know it's unstable to what exactly. I mean, the monopole in general drives it to some strong coupling regime. But the most natural expectation is it probably induces something like spontaneous symmetry breaking phase. Okay? And the nature of the spontaneous symmetry breaking phase that you can naturally get out of this theory, you can also figure out from the symmetry properties of your monopoles and the Dirac fermions. And in particular, one of the many possible symmetry breaking order is called a tetramerized phase. So this is it's a singlet phase, as an SU4 singlet phase that breaks some of the lattice translation symmetries. So one of the pattern is here. So all this pink or purple triangle includes 4 SU4 spins that form a singlet. So you can see that this pattern obviously breaks the underlying lattice symmetries. And this symmetry breaking pattern actually is observed numerically in this paper. If you deform the nearest neighbor Heisenberg-like SU4 model, if you add some further neighbor coupling, you can actually stabilize this as a ground state. So basically, the numerically observed spin orbital liquid cannot literally be this minimum Dirac spin liquid. Okay? So the non-trivial question is exactly, but what is it? Suppose it is really a spin liquid, which looks like it is. So what is it? Well, there are 2 possible alternative scenarios. Well, there are more than 2. The 2 are the minimal ones that we can think of, basically. So the first one is that it turns out you can do a more complicated Parton construction to get an alternative U1 Dirac spin orbital liquid. So again, the low energy theory is described by 8 flavor QED3, but now in this theory, all the monopole provisions are forbidden by lattice symmetries. So it's a perfectly allowed state, but even conceptually to construct it turned out to be pretty complicated. For example, one thing you can do is instead of directly writing down a mean field hopping Hamiltonian for the F fermion, you further fractionize the F fermion into 3 auxiliary fermion G in the anti-fundamental representation. So you take this 3 anti-fundamental, form a fundamental, which is F, and then you have to arrange those G fermions into some somewhat complicated mean field theory and so on. So it's a complicated construction, but the state does seem to be allowed. So for some reason, for various reasons, this scenario doesn't seem to be extremely natural, but okay, it's still possible. So there is a probably more natural scenario, alternative scenario, which is that the U1 gauge symmetry is actually Higgsed down to Z4. For example, you can have some 4 fermion term in your quote unquote mean field theory, even though a 4 fermion term is not really a mean field. But it does, you could consider breaking this U1 gauge symmetry down to Z4. So once you Higgs the U1 gauge field symmetry down to Z4, the Z4 discrete gauge field couples weakly to the Dirac fermion in the IR. So any discrete gauge field couples weakly in the IR as long as they are deconfined. So then you get a stable Z4 Dirac spin liquid. So that in principle may be consistent with the numerics. So one thing interesting about this scenario is that in this case you get some interesting theory of phase transitions to nearby symmetry breaking orders, and there's a somewhat similar story on the square lattice, but with some subtle difference as well. I think on the square lattice in this work, for example, the phase transition is a non-relativistic critical field theory. While in our case, it's a pretty simple relativistic conformal field theory. All right, but these are just 2 possible alternatives that are consistent with the current numerical evidence. To know exactly which scenario is relevant for the real case, or if it's some more complicated scenario, that requires further numerical works on this SU4 lattice model. Okay. So the short answer is we still don't know exactly what's going on. And I think I'm running out of time, so let me just end here. And this is the summary. So what I want to emphasize is that symmetry properties of monopoles in Dirac spin liquid gives you a rich story, stability of Dirac spin liquid and various competing orders. And for SU2 spins, the minimal Dirac spin liquid states are stable on triangular or possibly cognate lattices. But for SU4 spin, more work definitely has to be done. The minimum theory doesn't seem to suffice. So that's my talk, and thank you.
Thanks for your interesting talk. I think we already have a question, Subir.
Oh, hi, Chong.
Hi, Subir.
So going back to the triangle lattice case.
Yes.
Sorry. Is that choice sufficient to get all the monopole?
Sorry, Subir, you were breaking up. Can you repeat your question?
Can you hear me now?
Yeah.
Okay, so you have this quantum spin Hall master, I guess one slide earlier. Yeah.
Yes.
That's a somewhat arbitrary choice that gives you all the possible monopole Berry phases, or you had to
Good. The important thing is this phase factor is independent of which monopole you choose. That's important. That's why it's sufficient to just choose one. So the quantum spin Hall turns out to be the most convenient one because it preserves all lattice symmetries. It only breaks spin rotation, but we know how to handle spin rotation already. So that's why we made that choice. Essentially, the idea is you use the quantum spin Hall mask to figure out, for the quantum spin Hall mask, you know which monopole you're picking out. You also know what SO6 matrix you are multiplying it for any symmetry operation. That way you can figure out this U1 phase factor, and then you use this U1 phase factor for all the 6 monopoles.
So this breaks this is the unique mascom that doesn't break any lattice symmetry, but it breaks spin rotations.
Yes.
Okay. And then when you're doing the rotation, I'm confused what was rotating where. So you have these charge centers.
Yes.
Here. So there's a charge center as Q delta equals 1. And now where is the monopole? The monopole is completely delocalized.
Yeah. So the I think the simplest idea is that you imagine putting the monopole somewhere here. It doesn't really matter exactly where, but imagine having the monopole somewhere away from the charge center, and then you just do rotation. The idea is anything away from charge center, all the charges away from the charge center comes in integer multiple of 3. So it doesn't contribute to any net angular momentum. So it's only the charge at the charge center mod 3 that matters.
Right. Okay. So that's what I didn't get. Okay. All right. Great. Thank you.
Sure.
Yeah. Could I just ask about this NF=4 theory? It seems to be a very subtle question whether it's within the conformal window or not. For example, in Appelquist's original work, they basically found that already NF=6 had broken symmetry, and then there were various improvements. When I just looked at the paper by Koitikov and Teber, and they, after some improved resummation, seem to conclude that NF=4 is not conformal. Like their n critical is something like 5.5.
Yeah. So I think so. This work is a lattice Monte Carlo one. I think that's the yeah. Okay. That I think they've done a pretty careful. Well, okay. Reasonably careful job in taking the continuum limit properly, and so that's one thing. The other thing is
I mean, if it's extremely close to being on the edge of conformal window, it may be incredibly hard to tell.
Exactly. So that I should comment on that. What we cannot rule out is that it's not conformal. It just has a very large correlation length. That we cannot rule out. In fact, it's it's quite plausible that NF equal to 2 is like this. It is of that sort. Because in this lattice simulation, for example, even NF equal to 2 appear to become normal. But from various reasons, many people, including me, think that NF equal to 2 is probably just have a very large correlation. It's like a walking coupling.
Yeah, that may be extremely hard to tell. I mean, in 4 dimensions, people, of course, have been fighting for years to pin down the lower rates.
Yeah. So so NF equal to 4 we don't know at this point whether NF equal to 4 belongs to that kind of thing. For the purpose of studying quantum spin liquid, it probably doesn't matter because you never really go to very low, zero, absolute zero temperature. So as long as your temperature is not ridiculously low, it's fine. But conceptually, I agree. It's an important question that has to be resolved. I mean, people are trying pretty hard to do bootstrap on this theory, and
I see.
We'll see how things are. So far, not much has been that much has been obtained there, but we'll see.
Okay, I'll find this paper and post it on chat now, just so people.
Also, Igor, a quick question, just to be sure. Chong was using 2-component Dirac fermion. Is that your?
No, I've accounted for that.
Fine.
Yeah,
Okay,
I mean, in this paper I'm about to post, they use 4 components, so it needs to be multiplied by 2. But
yeah.
Okay, thanks. Thank you.
Thanks, man.
See, do you have any other questions? Grisha.
I have a question related to the spin system. So so you said that so you can rule out the existence of monopoles using the symmetry. So so you basically for this you take the full system, not the min field, like not the min field.
Well, okay. So what? Yeah. Okay. So when I think about the monopoles, what I mean by the system is really an underlying lattice gauge theory. So forget about the spin. Just think about the lattice fermion with the lattice U1 gauge field. Right? That's what I'm really considering. So the Parton trick, you can think of it as a way to take you from the spin theory to a lattice gauge theory. So that's the viewpoint I take.
So, but maybe let me rephrase again. So you don't need to rely on mean field for this conclusion, right? Or you do rely?
I do. Yeah. I think when I say a lattice gauge theory, what I mean specifically is that I start from some free fermion on the lattice, and at the lattice scale, weakly coupled to the U1 gauge field. That's the only regime where my calculation is controlled, right? Of course, the underlying assumption is that's actually adiabatically continuous to the actual spin system, which that's what we mean by it's a Dirac spin liquid.
But you say there are several ways to take this mean field, or?
Oh yeah. There for example, on this triangle lattice, you can take this mean field, or you can take no flux, in which case you get it Fermi surface and so on. Even if you want to get Dirac fermion, there may be multiple ways to do that. And in general, the thing is, if you include the full fluctuation, in principle they're all equivalent. But if you require your gauge field to be weakly coupled, they may correspond to a totally different phase. Because you are only exploring a small coupling, a small region in the coupling space, basically.
Oh, I see. Okay, thank you.
Sure.
Okay. Any other questions? Baptiste?
Yeah, maybe just a fast question. In your graph about deconfined criticality and spin liquids, we see that square and honeycomb, which are the two bipartite lattice, does not host a spin liquid phase. Is there a link between the fact that they are the bipartite lattice and not the triangle Darwin? Yeah.
Yes. What happens is that it turns out that that if the underlying spin on mean field theory has or can be deformed to a particle hole symmetric point, one can show that alone requires the existence of a trivial monopole, it turns out.
Okay.
And of course, that's in general, if you have nearest neighbor hopping only, then that's possible only on bipartite lattice. So there is a deep connection, which we did discuss in our paper, and I just skipped that here. Yeah. But this doesn't apply for the SU4 case. So for the SU4 case, I described on the honeycomb lattice. But if you have SU4 fundamental per side on the honeycomb, there is no particle hole symmetry because you're at quarter filling. So that's why it's a different discussion.